Good afternoon. It's great to see you all here. I'm Phil Duxbury, Dean of the College of Natural Science and your MC for today's event. Thank you all for joining us on this momentous occasion for the Department of Chemistry, the Department of Mathematics, the College of Natural Science, and the whole university. As we honor Piotr Piłczuk and Guowei Wei as MSU Research Foundation professors. I'd like to extend a special welcome to Piotr and Guowei's family members, colleagues, and lab partners who are here with us today. Our program will touch briefly on the creation and importance of the MSU Foundation Professor designation and the long-term impact that these prestigious positions have on the continued excellence of the university environment. Let me personally congratulate Dr. Piłczuk and Dr. Wei for their achievements to date. They're always great to talk with, and that will be recognized by these prestigious professorships. Following a few remarks and brief introductions about Piotr and Guowei from their respective department chairs, we will hear from our two honorees and have their formal investitures as MSU Research Foundation professors. Finally, Dave Washburn, Executive Director of the MSU Research Foundation, will provide a few closing remarks on how and why these professorships came to be. With that, I would like to turn the program over to MSU Vice President for Research and Innovation, Doug Gage. Doug, thanks for being here.
So thank you, and thank you, everyone. I'm very pleased to be here this afternoon to really honor Drs. Piłczuk and Dr. Wei. This is an amazing opportunity to really recognize their achievements. It's something we don't do often enough at MSU, and I think this is a way that we can really celebrate what they've accomplished so far. The MSU Research Foundation professorships are in their 9th year, and they've become a very significant contribution to our academic environment at MSU. These professorships serve as a flexible and ongoing resource that allows us to be responsive to the university's strategic needs, and really, the important thing is that they recognize these individuals who contribute so much to our reputation as a university. In a few minutes, you'll hear from our two honorees today. I look forward to that. And both of these individuals are part of a really outstanding group of MSU scholars who contribute at an extraordinary level to this in the search for new knowledge. And as a result, each of them actually help attract additional scholars to MSU. I think that's another thing about honoring faculty of this caliber, is it really sets the stage for the next generation who will come and join us. Both Guowei and Piotr are really highly influential, both nationally and internationally. Each has been a role model to early career faculty and really help us create that environment of excellence. Thanks to funding from the MSU Research Foundation and the Office of College of Natural Science, as well as the Office of the Provost, the university will provide a permanent recognition of their achievements. And we hope that ultimately that they will inspire others, MSU friends, donors, and alumni, to provide permanent funding in the form of endowments to support all of our top scholars in perpetuity. This is a great day of pride and celebration. And with colleagues such as Dr. Piłczuk and Dr. Wei, I believe MSU can look forward to many more years of success. I'll now turn the program back to Phil. Thank you.
Thanks, Doug. As you just heard, named faculty professorships are very important for the individual and for the university. We're in a very competitive environment, and we're always looking to reward our faculty and make sure that they want to stay at Michigan State and that we are competitive with our peers. Endowed positions are the hallmark of every great university and critical to increasing our competitiveness nationally and internationally. These professorships are awarded to only the most outstanding faculty in the university and are meant to recognize exceptional leadership as well as research productivity. MSU Foundation professorships are held by the recipients throughout their academic career, so you've got these denominations for life, throughout their academic career at Michigan State, I should say, and include a 5-year unrestricted stipend. MSU Foundation research professors are expected to continue to pursue a program of research at the highest level and to take on leadership roles to enhance the intellectual life of the university. Having Piotr and Ngwowe as MSU Research Foundation professors will help guarantee continued growth of quality and impact in their departments, the college, and their respective fields. The impact of these professorships is much broader, though. Having strong faculty members on campus helps ensure that we have a strong group of students and postdocs, and that we can attract other strong faculty members. Together, all of these effects help ensure that our future alumni will have the education and experience they need to compete for the best jobs and lead the nation and world in maintaining and building scientific leadership. Piotr and Ngwowe, congratulations again. We're looking forward to more great things. Next up is Tim Warren, a Barnett Rosenberg Professor and Chair of the Department of Chemistry, who will introduce our first honoree, Piotr.
Thanks, Phil and Doug. It's really quite an honor to be able to introduce my colleague, Professor Piotr Piechuk, who's a university distinguished professor and now an MSU Research Foundation professor. Actually, he's been an MSU Research Foundation professor for some time, but COVID kind of got in the way of us having the celebration all together. Before I introduce Dr. Piechuk and his work, I really want to share my sincere thanks to the MSU Research Foundation. It's through awards like this that really helps to nurture and sustain excellence at the frontiers of research that we do here at Michigan State. So I'm honored in a really special way to be able to share some words on my colleague, Professor Piotr Piechuk. Piotr received his master's and doctoral degrees in chemistry from the University of Wrocław, Poland in 1983 and 1988. Through postdoctoral and faculty appointments in Poland, Canada, and the US, he's had the opportunity to work with many leaders in the field of physical and theoretical chemistry, such as the 1986 Nobel laureate John Polanyi. He joined Michigan State as an assistant professor in chemistry in 1998. And with a truly meteoric rise through the ranks, he was promoted to associate professor with tenure in 2004, and then just 2 more years to full professor in 2004. And it didn't stop there. Just 3 more years, and he was promoted to the very special rank of University Distinguished Professor in 2007, representing less than 10 years since his initial appointment at Michigan State. I also should add he's an adjunct professor in the Department of Physics and Astronomy. And so with this really rapid rise through the ranks here at Michigan State, it won't be a surprise to this audience that Piotr is a highly respected, world-renowned theoretical and computational chemist and physicist. Of particular importance are his contributions to coupled cluster theory, as applied to many electron systems and atomic nuclei, his work on intermolecular forces, and applications of computational approaches to problems ranging from chemical reactivity in gas and condensed phases to molecular spectroscopy and photochemistry. Piotr has developed methods that enable the computation of extremely accurate predictions of molecular species that not only enable a deeper understanding of the known, but help experimentalists to imagine what has not yet been discovered. His methods are widely employed. He's a co-author of the widely used General Atomic Molecular Electronic Structure System, or GAMES, software package where these highly accurate methods can be used by many. And in fact, I'm kind of sorry that I don't have a picture here because he's also very proud to be banned from another computational package called Gaussian for his excellence in the contribution to the games package. And if you want to see Piotr in a slightly different outfit than he's wearing today, I encourage you to go to his website. He looks like a bandit from the Wild West, saying that he's outlawed for doing chemistry without a Gaussian license. So, you know, by the numbers, his work has massive impact. He's got more than 230 papers with over 16,000 citations with an H index of 71. So this is the number of papers that's been cited more than the 71 times. Truly remarkable. Piotr is a world traveler. This comes by way of his science. And as such, his eminence is also recognized by his selection as a member or a fellow of a number of international organizations that include the International Academy of Quantum Molecular Science, the European Academy of Sciences, Arts, and Humanities, the Sloan Foundation, and he's also a fellow of the American Association for the Advancement of Science and the American Physical Society. Few faculty have this type of impact alone, and Piotr's no exception. Support from the MSU Research Foundation helps to maintain and sustain a strong group of graduate students, postdocs, and visiting scholars. In fact, Piotr is known for the close mentorship of his students that enables them to contribute at the frontiers of these fields alongside Piotr, as well as to travel the world to present their work. Piotr is extremely supportive in this regard. Former department chair John McCracken has shared with me that Piotr has an amazing ability to turn students who join his group into top-notch independent scientists. Piotr, congratulations on this wonderful recognition by our department, NatSci, and the MSU Research Foundation. Along with our audience here, I truly look forward to learning more about your science and your journey of excellence.
All right. I'm speechless. You know, after this kind of introduction, it can only get worse. But anyway, I'll try. Well, first of all, thank you, Tim, for this wonderful introduction. And I'd like to also thank Phil and Doug for their kind words. So this is my first slide, which sort of says that I think that our group is working in the area of quantum chemistry and physics as applied to atomic and molecular systems, also to atomic nuclei. Sometimes we go to condensed matter. This picture in the middle is a lovely picture of chemistry and BPS. I'm appointed in both departments, so I think it's an adequate picture for the situation. But I have another picture here that I think Tim wanted to show you, which is sort of shows me in a sort of certain situation as a wanted person, not in a positive sense, but in a negative sense, wanted for practicing chemistry without a Gaussian license, and I'll try to explain to you what it means as we go. But before I continue, let me begin by expressing my special thanks to several people. I'd like to thank our former chair, Professor Rob Maleczka, who is here, and Dean of our college, Phil Duxbury, for initiating the process of nominating me for MSU Foundation professorship. That's how I understand the process. I talked to Rob a little bit about those secrets. I would like to thank Phil again for submitting the formal nomination. And then I would like to thank also the former interim provost, Teresa Sullivan, and former vice president for research and innovation, Professor Stephen Xu, for approving the title, which is was a very great news to me. Last but not least, I would like to thank MSU Research Foundation and its executive director, David Washburn, here, and vice president for research and innovation, Doug Gage, who is here, and dean of our college, Phil, who is also here, for providing me with the generous support of my research program. It's really great to feel supported in all these ways. So I tried to create a slide here, which maybe has too many words. Some people who know me know that I am usually writing long emails and saying too many things. Nevertheless, I am trying to summarize all of our work on a single slide, and then I'll go into some additional information. So the heart of our research effort indeed is the development of new ab initio, we should actually say ab initio, that's a Latin word, methods for molecular electronic structure and nuclear physics. In other words, we're interested in solving quantum mechanical equations for many-body systems, many fermion systems such as electronic systems or nuclei. What it means is that we are developing methods that allow us to obtain highly accurate, predictive, as we say, and systematically improvable methods for ground and excited electronic states. In our group, we are not focusing on any particular type of chemistry or physics. We are rather trying to think of ourselves as being tool makers for solving a wide range of problems in various categories. So it could be ground states, could be excited states, could be closed shell systems, could be open shell systems, could be small molecules, which we can do very precisely, essentially exactly, and larger systems with dozens or hundreds of atoms. All of these methods, as Tim already said, are usually focusing on the idea of using the Kappa cluster wave function ansatz, and the byproduct of our effort, in addition to publications that people can read, is software. So we are indeed involved in the games package. I'll say a little bit about it in a moment, which is widely used, as you can see the numbers. And also, in recent years, we decided to share the fruits of our labor by sharing our codes on GitHub, which is an open source. Then everybody in the world can use it. You don't have to pay for it. I know we like making money, but I think this is actually an area where you would like to empower people around the world, because not everybody can buy software, for example. Since we think about the many-body problem broadly, we do not consider electrons to be so special. There are other particles in this world which are fermions, so we can develop these methods as methods for many fermion systems, and an example would be protons and neutrons that form nuclei. Now, having access to our own powerful tools, we can then study all kinds of interesting problems, quite often of interest to experiment, sometimes ahead of experiment, so we can guide experiment and provide information which is harder to get experimentally, and those will be problems in areas of spectroscopy, photochemistry, photophysics. We really like studying reaction dynamics and mechanisms because we are able to provide very accurate molecular potential surfaces of ground and excited states, and that starts with small molecules of interest to combustion or cold physics or ultra cold physics. Those are tiny systems which you can study really accurately, and we can go all the way to systems of interest in organic, inorganic chemistry, bioinorganic chemistry, and so on and so forth, sometimes materials. I have this old interest in interlocular forces, and once in a while this comes back because molecules do interact weakly, and you would like to describe it as well. That's how matter is formed, really. So that's an important topic too. Now, why do we try to address these problems so broadly? Because my way of thinking about sort of matter around us is that those are all many-body systems. If you really look at what nature is, the one that we are studying, those are many-body systems. We have nuclei that consist of protons and neutrons. We have atoms, molecules, clusters, condensed matter systems that consist of electrons, and nuclei then treated as point particles really that provide an external potential for those electrons to move around. Okay, so we can think about the whole enterprise as essentially one many-body theory. Okay, where where we have to of course pay attention to the fact that there are differences, like for example in length scale, nuclei are in the femtometer regime. Okay, molecules are in a nanometer regime. So we're talking about orders of magnitude of a difference. The same with energies. If you look at binding energies of nuclei or excitation energies in nuclei, they are in a mega electron volt regime. Now, in chemistry, in molecules, we're talking about electron volts or sometimes fractions of those. But all of this still can be treated with a single approach, which we often refer to as the microscopic approach, the bottom-up approach. We start from constituent particles with electrons or, say, nucleons, and then so we have to, of course, define what our particles will be. That's our first point. Then we define interactions. Now, in chemistry, that's actually straightforward. As Professor Fritz Schaefer says, it's just the Coulomb law. Okay, we know how electrons interact. Once in a while, we have to go beyond that because there are systems in which we have to incorporate relativity. Then Coulomb law is not enough. Then we will do that, but that's still fairly established. We don't face challenges that people in nuclear physics face, where you don't know actually the nuclear-nuclear interactions precisely. And nevertheless, there's been a great progress in nuclear physics, and thanks to the use of what is called the effective field theory and which is a sort of byproduct of QCD, quantum chromodynamics, one can actually write expressions that are fairly accurate these days. Once you have those two, you build the Hamiltonian. Hamiltonian is an energy operator, so we know how to write it. That's an undergraduate knowledge, essentially. And then, of course, we can have two forms of it, bare or effective. We prefer bare, because that means that we start really from the ground up. But once in a while, we don't want to do this for various reasons. It may be too expensive, or we don't want to do it, or we don't know those interactions well enough. Then we build what is called the effective Hamiltonian. Once we have all of this constructed, we go, of course, to writing the appropriate equations of motion or state. Then we work on these equations, try to solve them, and I'll say a little bit about that. And then, of course, since the whole thing is complex, you know, even a small molecule like water has 10 electrons already, and they interact. If you think about a protein, that's many more. Of course, that means that you really, this is a complex problem. You cannot solve it with pen and paper. You have to resort to computers, and those computers are, we like, of course, those which look like that. But if they don't, actually, we also spend some time on developing software which actually can be run on a laptop. I don't know where is my laptop here. It's somewhere. Sarah knows. Anyway, we could run it there too, probably, right? Not everything, but some things. So we pay attention to a variety of computer architectures to make sure that people are not tied up to having access to these powerful sensors, which are very few in the world. Okay, so what is that we really are solving? We're solving the many particle Schrödinger equation in our case. So in quantum chemistry, we call this the electronic Schrödinger equation, which is an eigenvalue problem, as we say. You have the Hamiltonian acting on the wave function, producing the energy times the wave function. Wave function is the function that contains all the information about the system of interest. So you have to solve for it, okay? The part which is easier is to write the Hamiltonian, because that's an energy expression, essentially, kinetic energies and potential energies of electrons and nuclei. You just write it down, and then you have to somehow solve it, okay? Once you, so we get energies right away, and then we also get wave functions from which we can construct reduced density matrices and compute properties other than energies. So essentially, we can get information about anything we want. Anything, as Don Truller, one of my collaborators and good friend in Minnesota, would say, anything we can write the formula for, we should be able to calculate, okay? And that's the sort of philosophy that we have, that we always think that if there is a formula, we should be able to get to it somehow, okay? But of course, if you do it in chemistry, that means that we can get molecular structures, we can get potential energy surfaces that form essentially a force field for the motion of atoms in a molecule. We can compute reaction pathways. For a chemist, that means that we study various structures that show up on the way from the reactants to products, various transition states, local minima, and all that. Okay, so we can determine in a qualitative sense what the reaction is, whether it goes, for example, this way or that way. But we can then characterize it also quantitatively, meaning providing the appropriate energetics and all that. We can study excited states, simulate spectra. You can see that this is theory, this is experiment. We can do well when we push hard enough. But as I already mentioned, Schrödinger equation obviously is a fundamental equation of quantum mechanics, so it applies to everything else quantum, and that else in our case is nuclear physics. So we write the same eigenvalue problem. The only difference is that now our Hamiltonian is different. Okay, and it's an effective Hamiltonian actually, because protons and neutrons are not elementary particles, they consist of quarks. Nevertheless, we can write down the formula. We will end up with, say, 3-body or 4-body interactions, more than 2-body interactions in chemistry, but that's all very straightforward for us, believe it or not, because we use the language of second quantization. And in second quantization, writing all these operators is the same effort. The only thing we cannot do in our group is to, say, determine the matrix element, as we say, of that Hamiltonian. So that's why we need our nuclear physics colleagues who know how to do it. They give us the Hamiltonian, and then we'll do the rest of the work. Okay, that's what we actually did. So that also says that we sort of try to work in both areas at the same time, because many-body techniques in one area can be transferred to another. Kappa cluster theory is a good example. It was initially suggested in 1958, after the exponential ansatz for the wave function was discovered in 1957, in the context of nuclear physics. It did not really succeed there. It was not pursued because the authors I knew, both of them, Kester and Kimmel, they did not think that this is practical enough. Well, a few years later, a young person from Czechoslovakia at that time in Prague, Jerzy Čížek, one of my mentors, said, well, this is actually a solvable problem. He showed how to do it, and then it became a very successful method in quantum chemistry. And we essentially returned the favor, my group, between 2004 and 2013, we published many papers in nuclear physics showing how to use kappa cluster theory to solve the nuclear many-body problem. So essentially, we brought the method home, as some people say. Okay. So how do we work? Well, we start as with the fundamental equations, the Schrödinger equation for a problem of interest, and then we have to find a formula for the wave function. Otherwise, it's some sort of a generic expression that we don't know what it is. So we have these various exponential forms. That's for the ground state. That's for excited states or electron-attached or ionized states. That's for states which mix up together in quasi-degeneracies. These formulas are not a guess. Sometimes, it is still in the textbooks or in physical chemistry where you suggest that you should use variational principle and guess the wave function. No, we don't do that. There are many theorems that were proved over the years how the wave function actually looks like. So all these equations are derivable from fundamental principles. So we take them as they are, and then we try to work with them. Okay? Working with them is actually fun. That's the biggest fun, I think, in our work. I think my students can confirm that. Namely, we use very nice mathematical techniques, such as Feynman diagrams, okay, which exist in the many-body theory under the names of Goldstone diagrams or Hugenholz diagrams. Those are essentially diagrams that were transferred from QED, or quantum electrodynamics, to many-body problem. We can use algebraic techniques, which are based on second quantization, Week's theorem, and all these nice things. We can use Uti's diagrams for spin adaptation. That's for angular momentum recoupling, which I actually did use a lot in the 1980s in Poland for intermolecular forces. Once we are done with all of this, we create programmable equations. Those will be now equations for the parameters of the wave function you have to solve for. And when I say now how complex the problem is, well, it is really complex, because when you think about a typical kappa cluster calculation, which is a realistic calculation, you talk about millions or hundreds of millions of parameters that you have to solve for, and those equations you are solving are actually not linear. So we have to spend a lot of time thinking about algorithms. How are we going to deal with that kind of, how are we going to store that information? Define the equation itself, and then how are we going to solve? That's what we do. Once we are done, so that's our little secret in those few offices that we occupy. Once we're done, we end up with software that now we can share with the rest of the world through games or GitHub. So thanks to these actually software pieces, our impact on the field is bigger than what publications alone would do. That is, people can not only, recently we published a paper with Kartik where actually we provided software before the paper was accepted. So the reviewer could actually run our codes and decide whether we are saying in the paper is right or wrong. Okay? So as a result, several methods, I'm not going to go into details here because I don't have that much time, but now there are several methods that became sort of standards or commonly accepted methods in quantum chemistry, like completely normalized kappa cluster approaches or equation of motion kappa cluster approaches for ground and excited states, like active space kappa cluster methods, or approximate coupled pair methods, which are very clever single reference approaches for strongly correlated systems. By that I mean problems like metal insulated transistors, which are very hard to describe. Otherwise, I did some work a long time ago on state universal multi-reference kappa cluster. We showed people how to use it. And with the help of our colleagues in Nanjing, the university in China, we actually did develop a methodology called the clustering molecule, which allows you to reduce the scalings of these methods. You have to realize that these methods have their costs. There are polynomial costs with the system size, but with certain tricks, realization that electrons in molecules can be localized, we can actually replace these costs by linear scaling or even sublinear scaling. Well, then you can really go to very large problems almost without loss of accuracy. Okay, and in recent years, especially after I received my new title, we worked on trying to build new standards or emerging standards. They're called CCPQ or various semi-stochastic approaches and so on, that allow us to actually approach the exact limits of the solutions of the Schrödinger equation, numerically speaking. So we are very happy about this development. It's being actively pursued. Now, what does it mean to be involved in games? Well, you can see this paper published in 2020. When you publish a paper about a popular code like this, in 3 years we get close to 800 citations. That's what happens. So I recommend that you get involved in this. That's a good way to improve your metrics. Okay, this is a code which is maintained and officially distributed from by Iowa State University by Professor Mark Gordon there. But in our group is responsible for the entire section of this code. It's a very large section that allows us to perform all kinds of kappa cluster, equation of motion kappa cluster, and local correlation methods in games. That's the user base, 150,000 plus. And this gives an opportunity to members of my group not only to publish papers, but also to get listed in the output of every games run in the world. Anybody who runs games right now will see the names of Emiliano de Ustova, our former grad student, Jeffrey Gore, our former grad student, Karol Kowalski, my first postdoc in MSU, Wei Li, who is the professor in China right now, was a postdoc, Jesse Latz, Ilias Magulas, Juin Shen, who is here in the audience, Marta Boch. They are all being known to the world as developers of this popular code, and Michigan State University name, by the way, is also listed. So everybody sees that name now in all those multiple uses. And we over the years introduced a lot of methods. I'm not going to read this, but I just to make sure that I'm returning the favor of becoming an MSU Research Foundation professor. I'd like to mention that the ones in magenta, those are the ones we introduced after we got the title. So as you can see, it's a significant fraction of the effort. And as I said, we also distribute our codes on GitHub. That's a newer effort, but I like it. It's an open source. It's in the sort of in the spirit of what we are doing these days, sharing the knowledge as broadly as possible. So we have our page. There are 4 different packages in it. One of them is plugin to Sci4. Sci4 is another popular code used by thousands of researchers in the world. Okay, the plugin means that you download Sci4, you download our CCT3 plugin, that's how we call it, and you can run them together, and then you can simply improve the functionality of Sci4, enrich it by these extra methods that we developed. That's one idea. Another, and actually this was done, I should say, by Emiliano de Ustova when he was our grad student, and Juin Shen, who is here in the audience. We also have this package, for example, called CCPy. I'm very impressed by this package because it does perform about 30 different quantum chemistry computations, and it was pretty much single-handedly written by Harti Gururangan there, okay, in the audience, in Python with the help of NumPy and Fortran to improve performance for the most demanding parts. It's an amazing package. That's a picture of Kartik. You can talk to him afterwards to learn how did he do it, because he did it in a few months. I'm just amazed that you can write the full package. It takes years normally to develop. So here's some secret that I still have to figure. Anyway, our methods are recognized as good enough to be also included in other packages that we do not develop. That is, other people who develop other packages, such as NWChem, QChem, MRCC, or Orca, decided that some of our methods are good enough for being added to their codes. So we have that sort of outreach. And as a matter of fact, we started discussions with Orca that has 60,000 users. Maybe we'll put our stuff there as well, helping them out. So all of this means that, of course, now I'll just give you a snapshot of that you can do a lot of interesting things with these programs. So, for example, we can study raw vibrational electronic and raw vibronic spectroscopies. This is an example, magnesium dimer, which is important in ultra-cold physics. If you look at, I don't know if you can see it well, but if you look at the black lines, that's an experimental laser-induced fluorescence spectrum, and the red lines are what we computed ab initio. No fudging parameters, no scaling, nothing. We reproduce these peaks to a wave number, and everything very accurately. Okay. Of course, in the case of small molecules like systems like magnesium dimer or a few atomic systems, we can do that kind of work, be in the wave number accuracy level. If you go to larger problems, we have to, reduce ourselves to maybe kilocalorie per mole. But we can study reaction dynamics, mechanisms, and all that. And finally, we can go to photochemistry. So this is actually an example of what really, where actually MSU Foundation money was useful, because we worked together with a few other groups in our department of Professor Marcos Dantos, Babak Borhan, Gary Blanchard, and Ned Jackson, and we worked on this interesting system they discovered, namely FRGSB, which is this organic molecule which in the ground state is benign, has pK of about 7, but when you excite it electronically with lasers, it gets pK of about 21. It is such a strong base that it can deprotonate alcohols in a solution. It's a remarkable discovery, and our group's role was, of course, to explain why is this happening. Here is another example of a collaboration with an experimental group in France, Dr. Valérie Blanchet and co-workers, where we discovered the dark state hidden in the Rydberg states, the double excited state, which explains how multiphoton ionization process is happening in azurine. And here is an illustration. We can go to much larger. Now this is boron defect in hexagonal boron nitride, where we were able to perform our high-level calculations to explain the photochemistry, photophysics, and so on of this system. We also, as I mentioned, introduced our methods to nuclear physics. That's the first paper in the longer series that happened in 2004. Maybe some of the metrics as a kind of a report, maybe, on what we did in the last few years. Okay, so yes, we published 23 new articles after I received the MSU Foundation professor title. Among them, there are 2 highly cited papers by Web of Science. There are 2 hot PCCP articles. PCCP stands for Physical Chemistry and Chemical Physics. They classify certain papers as hot, so that's what we ended up with. 3 journal covers, the best paper of the year in molecular physics, and we did improve some of our citations. So all of this was very helpful. Finally, of course, I have to say this. None of this would happen if I didn't have a fantastic group of researchers working with me. People who really are spending all the time. I'm mostly doing the talking, they're doing the actual work. Okay? You can see them here, and they're all here. Arnab Chakraborty, Karti Gururangan, who I already mentioned, Tianga Deng, Swati Priyadarsini, Ogniwa Handra, and Dr. Jwin Shen, who I also mentioned. But over the years, I, of course, worked with a very creative group of dedicated researchers as well. So those are my former postdocs, those are my former grad students. Altogether, I work with 16 postdoctoral and visiting scholars, 20 doctoral students, 13 of whom received their PhDs, 6 research undergraduates, and they are doing very well in their own way. Okay, Karol Kowalski, my very first postdoc, after he left our group, he went to Pacific Northwest National Laboratory, raised to the ranks, and now he is a laboratory fellow. So he is not only a group leader, but more than that. Laboratory fellow is like, I don't know, MSU Research Foundation professor at MSU, okay? Something like this, right? There's only a handful of people with that title of laboratory fellow out of thousands of researchers that work in that lab, okay? Jesse Edwards is a full professor at Florida AMU. Marta decided to pursue an educational career, so she works in St. Mary's Preparatory in Michigan, actually, and I read already articles about her, so she is doing extremely well. Arman, for example, is a full professor at Ege University in Turkey, a nice place, in Izmir. And you know, I can go through the list. This is Jeff Gore, who I mentioned, who actually, after being a student with me and then postdoc at Stanford, decided to go to Microsoft. And now he's a senior programmer and engineer at Microsoft. You know, and you can go through this list. Merrick's got tenure recently. Emiliano decided to choose a different avenue. You know, maybe a good alternative to the traditional career is to create a job for yourself. So he just started a new company. Okay, actually, with one of the former students of Alex Dickinson from this university and their colleague from Germany. They have this company, and they hope that they'll become, I guess, very rich soon. Okay, let's wish them all the best. Okay, at the end, I would like to say I prepared this map. I can skip you if you think that I'm talking too much already. But this is to recognize my mentors. You know my career, Tim summarized it. But I would like to say that I really wouldn't be standing in front of you if I didn't work with fantastic individuals who really allowed me to become successful. So I started in the University of Wrocław, an old university from 1702. Okay, I had a formal advisor in my undergraduate and graduate years, Professor Henryk Ratajczak, a world expert in hydrogen bonding. And he was a formal advisor in the sense that he just let me do whatever I wanted to do, which is kind of unusual. And I published about 20 papers as a result as a single author. Okay, so then I decided to change my field from intermolecular forces in Poland to quantum chemistry. I was invited to work with the legendary Professor Józef Paldus, who is a founder of modern electronic structure theory and many-body theory. He unfortunately passed away earlier this year, so he's greatly missed as a scientist and as a wonderful person. It's a personal loss to me. Then I returned back to Poland because they offered me a tenure track position. But I had this attraction to North America, and I figured I have to go back. So I went back to Arizona, worked with Professor Ludwik Adamowicz, then came back to Canada, this time on the faculty appointment, but with no tenure, in a sort of non-tenure system, working with Joe Paldus again. Then I was invited to work in Toronto by Professor John Polanyi, the Nobel laureate from 1986, also as a non-tenured assistant professor. And I taught general chemistry there in addition to doing research. It was a good experience before coming to MSU. Then I moved to Florida, getting south again, to work for a few months with Professor Rod Bartlett before landing a job at Michigan State University. Rod Bartlett is another giant in the field of many-body theory. So in the process of doing all these travels, you can see traveling much of the world, I got 3 citizenships. So I'm now a citizen of the United States, Canada, and Poland by birth. So with all of this, let me stop here. Let me thank the Office of Vice President for Research, MSU Research Foundation, the Office of the Dean, our department, and my colleagues who are all here, well, many of them are here, my group, current and present members, and I would like to now give my special thanks to my family, my wife Jolanta, who is my partner in all of this long journey. You can see how much we had to travel together, and our daughter Anna, who is pursuing her PhD, but it's not in chemistry or physics, it is in modern history. Okay, so we have now interesting discussions about history. So thank you again for listening to this.
Thank you, Piotr. That was fantastic. I couldn't read some of the equations there, so I'll have to get the script.
Okay, I'm good.
I'd now like to invite Keith Promislow up to introduce our second honoree, Guo Weiwei.
Thank you, Phil and Doug. It's great to be here. I remember when we were negotiating this, and I'm very happy that it's to come to fruition. When I was very young, I was given advice: never share your computer with a computational chemist. Let me add a corollary: never share your investiture with a computational chemist, as they'll just suck it dry by the time you're up here. So Guo Wei and I arrived at MSU at almost exactly the same time in the early 2000s. So it's really a pleasure for me to add the perspective of the math department on this on the important occasion of his investiture as an MSU Research Foundation professor. Professor Wei is an applied mathematician, specializes in applying novel computational methods to problems in molecular biology and drug design discovery. His work is deeply innovative. He merges neural networks, machine learning, with very novel approaches to topological and algebraic formulations, and brings this fusion to bear upon computational biology. He has been very well honored. Among his many awards and achievements, he's been named a Fellow of the American Institute for Medical and Biological Engineering this year, 2023. From 2016 to 2019, he was the top winner of the Drug Design Data Resource Grand Challenge. That's sort of the Olympics of drug binding competition at an international level. That's quite an achievement. He received the Best Paper Award from the 2019 International Congress of Chinese Mathematicians. He's given an enormous list of distinguished invited lectures. He's received grants totaling more than $17 million, published more than 30 papers, and his H-index is 80, but who's counting? During the pandemic, it was quite transformative. I remember walking through the hall, there weren't a lot of people around, and I saw Guo Wei, early days, in his office, and he was tired. And you're all, well, are you feeling okay? Yeah, I've just been working very hard. You need to understand, Guo Wei's working is three levels log on my working very hard. So Guo Wei working very hard, it was very difficult for me to comprehend. I just looked at him, I said, he's not sleeping. I said, what? He said, well, so I've pivoted my team. We're working on COVID. So you need to understand that Guo Wei was brought up in Hunan, where the pandemic first had major impact. And so it was deeply, you could see in his eyes the impact on him. And so I understood what he was going to do. I almost had a little bit of pity for the virus, what was about to happen to it. And so he turned his machinery, this novel fusion of topology and algebra and deep learning, and he analyzed many things, including the mutation data of SARS-CoV-2. So I always felt about a month or two ahead of the news, because Guo Wei would tell me what was going to happen. Hey, you got to think about this for a second. You give me the code for a virus. Guo Wei can compute its future. The accuracy is almost perfect, demonstrating in June 2020 that the mutations were leading to a more infectious virus. In 2021, his group correctly predicted the vaccine viral breakthrough due to mutations, not just the existence, but the mechanism. In 2022, he accurately forecast the emerging dominance of the BA2 and the BA4/BA5 variants. You can see what's going to happen. A virus is a piece of code, the right mathematics, its future is deterministic. Turn that over in your head, for good and for bad. That is an amazing statement. In short, Guo Wei is an applied mathematician who develops cutting-edge techniques to attract real-world problems. As Doug spoke, his group attracts many visitors and collaborators to the department. He greatly enriches the atmosphere. He consistently recruits excellent graduate students and postdoctoral researchers who have gone on to have great impact. And I'm just going to let Guo Wei tell the rest of the story about the exciting work that he's doing. Guo Wei, it's a pleasure.
Yeah. Oh yeah. Thank you so much. Thank Keith again for his support and the company in the math department. It's actually it's not easy to go through so many years in the math for some reason, you know. And also for certainly I would like to thank MSU Foundation and thank the Dean's Office and so Phil, and also thank the rest of the department, the people for the supportive for me to really focus on the type of research on the particularly in the past 3 years. I really just really focus on the pandemics in the past few years, things like that. So I'm 100% in the math, but I also have a course appointments in the biochemistry, molecular biology, and electrical and computer engineering. I actually also thank the support and also partnership with other places like Pfizer and BMS and also FDA. Recently, we have a contract over there, and also a lot of different funding agencies, right? Now also last list, I would like to thank my team, and this is a picture taken like 1 year ago, something like that. My team, I always have one of the biggest team in the US in the math. So in the past many years, so I have my postdoc students, so they actually the ones get work done, and without them, I cannot stand here today. And also I would like to thank my former students, postdocs, about half of them, so is in the academy in the U.S. And also other people, they are industry. If they go to industry, for sure, you know, they like those ladies, they are make like $500,000 per year, things like that. Yeah, it's cannot compete with MSU, sure. So this is and also I thank other people, my collaborator, my collaborator in the bio domain with this blue color. So a lot of them, you see those people, you know, yeah, including, you know, show face here, and also people in the math department. So yeah, they are in this green color, include my actually former department chair Peter Bass. He actually gave me a lot of help when I come to the MSU. I come to MSU in the environment such that I don't really have a degree in the math, you know. I'm a person, I don't have any degree in the math. So, but my people, they have a degree in the math. So Peter Bass actually instrument such things. So actually, I'm very grateful for his support and for his help, right? And also I work with other people like pure mathematicians, Jie Wu, and also Yao, maybe some of you know him. He's a physics matter winner. So I also work with Yi Tong for many years. So we have work more than 15 years at MSU. So yeah, I also thank everybody to come here. Yeah. Mm-hmm. I just want to, I don't put any equation here, but I do want to give you a perspective of what's going on with my work. So this is the picture summarizes everything, like what Piotr just did a moment ago. And for sure, we do a lot of things in the all big scale, you know, everything about sequence structure, biophysics, bioinformatics, systems biology, and system physiology. I just list just a few things there, But I also work on a lot of deep learning, machine learning, algorithm, everything you can think about, generative AI, ChatGPT. By the way, I was the person who organized MSU's first data science, also machine learning initiative about 10 years ago, right? And this is unique to me because this is things you see, you can find thousands of people are doing this, join this two domain, doing things like that. But you may find just one group in the MSU combine these things with the rest. So that's my group. So basically most of our paper, I guess without the people in my group, other people, they cannot go through our paper. So that's the case in the whole world. Because we actually use a lot of math, so algebra topology, differential geometry, graph theory, geometric algebra, variation of PDE. So with this type of sophistication, so combined with AI, and also biology, complex biology, so basically only our group can read our paper. I'm sorry for that. Yeah. I mean, recently go through everything, okay? Yeah. So Chris just mentioned that, this is the test. So for the grand challenge in the drug discovery competition, we compete with the computation chemists, computation biophysicists all over the world for the drug discovery. Because the drug discovery, is about $200 billion per year business. So there's a lot of smart people there. So we actually initially get in there, and we actually was the best group for that part, just a small part, because we have a few mathematicians in my group. They really don't have any biology beyond high school. So I was able to work together with them to get this gold, things like that. And the next year we'll be a little bit better prepared, and I think you see we got a gold, all kinds of different places there. So that's the second year. By the way, people here, they are faculties in the U.S. State. So, and then next year we get a little bit better prepared, and then we also get to go to all the different places. Except for those ones we don't get it. Why? Because before they announce when they announce the competition, they don't have this category. Because my team over there from math and just get everything, dominate everything, and they feel so unhappy, uneasy. And then they create some category. Certainly we are not there, Well, this is after the competition, So this is things like that, right? So this is before pandemics, So when the pandemics now, we're looking back into pandemics, so we can summarize in like a chemistry, infrared spectrum. You have alpha, beta, delta, and Omicron, and BA2, and BA4, BA5. What is those things? So each one, this one is a 5-day infection in terms of meanings, okay? And then the other one, actually, the red ones are the people die, how many have 5-day averages. These are people there, they died from it. That's why we work extremely hard, because this thing is life and living. So what is the evolution mechanism? So we try to understand it. If we know the mechanism, we know what is going to be the next peak and what is going to happen in the next step. So that's something actually we focus on during the correlating. So, but the correlating is a small virus look like that with spike protein, membrane protein, things like that. This blue thing is the membrane of our body. It's like a cell membrane. And when the virus get inside our cell, it's just a release viral material, and then they get all kinds of things. I don't want to get into detail. But basically, the next 100 years, biologists still going to look into that. We take maybe next 100 years to really fully understand all the steps. But the big picture is that, finally the virus wanted to just reassemble the virus children again and get back and infect other people. That's how the virus propagation, the life cycle, right? So what is going on here is so complicated. So is there any way we can attack it? How to try to understand? So in the early of the pandemic, everybody actually government get somehow panic, and also a lot of research feel helpless. So what we try to say, okay, from mathematical point of view, we want to always, also physical point of view, we always want to simplify what is the major things. The way to simplify is this step. You see, you got a spike protein and it interacts with a human receptor, it's other protein. It's just a protein-protein interaction. If you focus on that without this step, the virus won't bother us, right? So that's the major things. If you simplify in such things without getting into this part, and then you can focus on this protein-protein interaction. So right before the pandemic, my team actually published a paper in the Nature Machine Intelligence exactly about the protein-protein interaction, how the mutation is going to impact that. So we're actually technically ready. And then we started to do that. So this is the things we tried to claim. We predict the important mutations size. So it's 455 and 501. I mean, this is our paper published in the middle of 2020. We actually stated in the abstract stated that 455, 155, plus 3 others out of 10,000 of amino acid is going to have a high chance to become to mutate into significantly more infectious coagulating strain. That's the statements come out at that time. Half a year later, we have alpha. This is the 501. And then we have a beta 501, gamma, and the delta 455, epsilon, whatever, omicron 501, and then omicron BA2 501 plus 455. So I made really remarkable prediction long before a lot of things come out. So before, at the time, people don't really understand what's going on. So that's one thing we did. We feel quite proud about it. And then actually, we also did a little bit more than that. We actually found out the mechanism of viral evolution. So what we said is, what is the picture? This is really just the term, right? And this is one particular mutation. Each one is one mutation. How this mutation, how many times being observed, you know? Like this one being observed roughly 50 times. 50 is over there, right? So, and then you can see the red ones are the ones, the mutations, they actually make this binding, protein-protein binding more effective. And then the blue ones are making this binding less effective. So you see the ones that make binding more efficient, they have a higher frequency being observed, right? They observe many times. This is very earlier. Total time is 50, but actually at this point we can see like almost 10 million times, right? This is a very earlier time we actually found out, and we said this is a natural selection. And it's going to, this whole thing, we point out this is natural selection through the binding. So certainly, you know, Darwin said the natural selection 150 years ago, but that natural selection is just at a population scale. Our natural selection is a population scale observation. We use AI combined with the molecular level of model. You have a molecular level model of understanding. So that's a different type of level of understanding. You know, really understand the mechanism. So this is the other thing. This is the first paper told the virus what is going to happen. Is the infectivity becomes stronger and stronger, right? But we keep looking at the data. We basically look at the data every day and accumulate all the data. And we realize the type of mutations, those are ones, most of the type of mutation, they make the virus actually binding energy become higher, to become the strength of the binding. But except for one that bothers us so much, look, this one make actually the binding actually loose. Why this one make it binding loose, still get into the top 50? That's something bothers us a lot. And then what we did is, okay, we look at 135 antibodies. Those antibodies come out from a patient, most of them they died, and we see what the type of antibody they have, and isolate that, and then you have a structure. And then we combine those antibody with the virus spike protein. And then we found it out, actually, most of these mutations out of there, they only disrupt, like Delta, only disrupt 35 antibody. But this guy is able to disrupt 85. So this is a clear evidence from this point of view. This is something like antibody resistance. Also, this is the mechanism, right? And then we look in the population scale. We look at you see, this is the 2021. We look into the US and Denmark. Those are the countries, they have first 2 doses of vaccination, right? And this is their vaccination population, statistics. Their vaccination rate is going up. And then you realize, this type of mutation rate, that's red guy, also going up. So there's a strong correlation of the vaccination and this particular mutation. So, and then we say, okay, this is actually the second mechanism. This is a vaccine breakthrough mutation. So in that way, our team actually discovered 2 mechanisms. One is the infectivity strengthening, other one is vaccination breakthrough, or antibody resistance. With these 2 mechanisms, what we can do? So we actually, with these 2 mechanisms, we can actually do further. We have put a paper out of there, that's a preprint. It's a February 10, we said that this is one particular, like a BA2, has a high potential to become the LAX dominating variant. Well, not only say this has become dominant, we also say this is the LAX one. So what has happened to that statement? Or we made a lot of other statements, all of them proved to be true. I don't want to bother you to go to that detail, So this is the WHO, they actually put a results over there, in the something, they actually give you showing the BA2 actually is the dominating things over there. Is right. It's something around, this is March. So basically our prediction is about 2 months ahead, what is going to dominate. So this is the one thing we did. And the next thing we did is also say, we also say this one, we have this put into the archive. I mean, the archive was so important. I mean, it's not a things you publish in the science literature that make any really important. It's the things actually sometimes you publish not important, even just a preprint is important. So we said actually May 1st, we said this is going to become a new dominating variant. And what happened to that, you see, this is also from the WHO. They have a statistics. This is the point, we said this is going to be an important variant at this spot here, So, but you can see later on, at this spot, they become really dominant. So among all the population, they become dominant. So this is we're actually able to, 2 months ahead, to predict what's really going on, a little bit more than 2 months. So what is going to dominate? At that point, the CDC was very interested in our stuff, and they asked us for code and for information. NIH also, over there, my program officer, they constantly forward our results to different places. And also, I talked to, because I work with BMS, and they actually develop an antibody. And then I analyzed their antibody. I told them, I said, guys, your antibody doesn't work. so I wrote to the vice president over there, VP, and they say, oh, we have a program going on. We already spent use thousands of $1 million over there, So they spend a lot of money on that. So they still keep working on, but later on they realize what I said is right. I actually able to 1 year ahead told them what's their antibody going to happen. So the antibody followed it with tons of money. Maybe I submitted it around tens of millions of dollars. Okay, sorry about that. So this is our prediction. We also predicted other antibodies. We said that there's going to be doesn't have any effects. So what I'm going to do future, this is the part I need MSU support. I feel it's very interesting supporting environment. So I wanted to predict what is the future, You see, this is the virus focus on the imaging dynamics. So what is going to happen for the next dynamics, right? Pandemics. So this is something I wanted to focus on. I wanted to know what is going to be most dangerous virus out of there and going to jump into human, right? So and also we wanted to develop vaccines for future pandemics. I work with Shofei on that things, and this is something is on my top list. That's what I wanted to do. Second thing I wanted to do is global warming is also a big problem. We have something tried to use mathematics, AI, tried to do genetic editing, and then we have drought resistance crops, and also we can use these things to design a new drug, things like that. So this is the second thing. We have been working on this for quite some time, have a couple of papers on that, and fortunately many other papers, right? So the last thing I wanted to do is the drug abuse is still very important problem in the U.S. It's about more than 100,000 people die every year because of drug abuse or drug overdose. So I didn't prepare good slides for that, but basically we use all kinds of fancy deep learning stuff with other all kinds of things to try to have an optimum drug candidate for this part, right? And finally, I want to thank you again for your attention. Yeah.
Thank you, Guowei. That was fascinating. I had no idea you could predict the evolution of viruses. That's amazing. And figuring out which ones are going to respond to antibodies, that seems like an incredible advance. With that, I'd like to invite Doug Gage back up, who's now going to do the heavy lifting.
You can wear this wherever you like. Thank you. Congratulations. You better take your glasses.
Not the swimming pool.
Yeah. It's now my pleasure to invite MSU Research Foundation Executive Director Dave Washburn to the podium to provide some closing remarks.
To Guowei and Piotr, on behalf of our board of directors at the MSU Research Foundation, congratulations on this great achievement. Really enjoyed your talks. I didn't understand half of them, but I mean, the impact is significant. So congratulations. The foundation, for the grad students or maybe others who haven't heard of us, we just celebrated our 50th birthday. We were created in 1973 by Clifton Wharton, who was the president of the university at the time. And here we are in the Wharton Center celebrating the work of him and many other scientists from this university. The foundation was started to initially help with fundraising, but we had a pretty big pivot in the late 70s when Barnett Rosenberg and his team came along and discovered sort of cisplatin and carboplatin. And the university took those discoveries, patented those, and licensed those to Bristol Myers Squibb. And that, I think, is what really changed the face of the foundation and I think the university. So not only did cisplatin and carboplatin save millions of lives because it was a cancer therapeutic, it generated hundreds of millions of dollars of royalty dollars that came in and were parked in the MSU Research Foundation. So in 1974 and 1975, the Research Foundation began its grant program. And since that time, our organization has turned around and handed back to the university close to $400 million in support for research purposes here at this university. So I think it's for a public university to have an organization like ours is very quite unique, and I'm just blessed to have the opportunity to run it right now and keep it in good hands. And so we're really thrilled to do the MSU Research Foundation professorships. Doug Gage and the research office and the provost about 10 years ago really wanted to do something significant in terms of attracting and retaining our very, very best faculty, and came up with this idea of creating these endowed professorships And our board of directors, and Doug's a member of that board of directors, thought it was a fabulous idea. And that's how this was started. And so I think we've done around 60 MSU Research Foundation professors. And it's just a hugely satisfactory thing to do for us and our organization. So congratulations to you all.
Thank you, Dave, and congratulations once again, Piotr and Guowe. And because the chemistry department, or some of the chemistry department, is here, it's appropriate to note that Barnett Rosenberg spent a lot of his research career in the chemistry department, and that there's a lot more opportunities for big discoveries, and there's lots of good things going on. So it's good to acknowledge that. With that, it's the end of the formal program, and those of you who have to get pictures taken, and Val will kind of tap you on the shoulder if you try to escape. And those who don't have to do that, there will be refreshments. So thank you, everybody, for coming.
Congratulations. Thank you. Okay. Good. Congratulations.
Thank you very much.
Hold that. Bring it outside your jacket.
Oh, I see. Yeah.
Very good.
Yep, perfect.
Perfect. Look right up here. Just
This must be the AI part. Thank you. Good.
Great. Perfect. And 1, 2, 3. That's good.
Okay.
Can't we just do this with AI now?
Great.
Okay, good. Good. 1, 2, 3. And 1, 2, 3. Scoot in just a little bit.
Hands on
Look at Scott first.
Hands on your side.
Great. Okay, good. Good.
Okay, very good. And 1, 2, 3. 1, 2, 3.
Well, cisplatin, cancer, this is of that magnitude.
Yep.
Of that magnitude.
Well, but even the point where he said, he knew when the next
Different temperature than up here.
This was for 5 years, and they combined my department with another one, and we'd go over to Epley. They were over at the building. So I didn't have a choice. They basically said, here's the job. Right? Okay.
I don't know how you built something.
You should check the overdrive. What is the course like?
Yeah.
But sometimes you have, because you point people on it, they point to the end of semester.
Yeah, actually yesterday I was kind of...
Is this the nice side or is this the nice?
I think this one is nicer in a way.
Yeah. Oh, but you what with me?
Well, no, they asked me actually to use this one. But it's...
Does this one say research? No. So then what?
So it's official.
You should be here. I think you're ill. I've been up all night working on this stuff. We're trying to figure out how to make it work. I mean, it's personal.
Yep.
It's very personal. I got it then. Yeah.
Yeah, some of them.
So that's maybe how you can.
Shadow picture, but the shadow box